So it's my great pleasure to have József Balogh here at this great seminar. He's a professor at UIUC and we'll talk about again covering cliques. Yeah, please.
Thanks for the opportunity to be here. I hope that I will repeat this thing that's happening today because the project that I'm talking about was initiated here 2.5 years ago at IBS, so I hope that when I come next time back then I will talk about something that was initiated during my visit. My co-authors, Jialin He, who was here, I don't know if he was just a visitor or a postdoc. He just emailed me this week that he got a job in Shanghai, something like that job. Eastern, is there Eastern University there?
Eastern China Normal University.
Yeah, sounds familiar. Robert Kruger, who was not here and he's at CMU now. Tan, who was not here and he is in Vietnam now, and Michael Wigal, who was visiting here as well. So let me start with some history of the problem. Maybe the problem can be initiated back to Kirkman from from the 18th century when he proved that a complete graph has a triangle decomposition, so it means that the edge set of the complete graph Kn can be partitioned into edge sets of triangles if n is equal to 1 or 3 modulo 6, and it's easy to prove that this condition is necessary because we need two things to happen. One thing is that the degree of each vertex must be even because if we have triangles sharing a vertex, then each triangle gets two vertices out. The other condition is that the total number of edges of Kn should be divisible by 3, and it's easy to check that if these two conditions are satisfied, if and only if n is equal to 1 or 3 modulo 6. An influential work of Wilson was extending this result for KQ decomposition, so the edge set of the complete graph was partitioned into edge sets of cliques of size Q. Here there are two conditions, at least for his proof. One of them that n should be sufficiently large compared to Q, and the other that the analog conditions that I mentioned here should be satisfied. So that there is no trivial reason that there is no KQ decomposition. And another related famous conjecture is due to Nash-Williams. Just in case, Nash-Williams is one person, not two. And he conjectured that we don't need a complete graph. A large minimum degree is enough for a triangle decomposition if the trivial obstacles does not kill the triangle decompositions. So this conjecture is still open. The current best bounds are due to Delcourt and Pósa, who proved that if the minimum degree is at least 0.28, and then there is this triangle decomposition, certainly assuming all the really nice conditions happening. And there was some interesting events about recently about the generalization. So it's a folklore conjecture that if the minimum degree of a graph is sufficiently large and there are no trivial objections having a KQ decomposition, then there should be a KQ decomposition. and Delcourt, Henderson, Lagerges, and Possel found a family of counterexamples where they proved that this conjecture is false. One has to put here an extra constant, and from the other direction that 1 minus Cn 1 minus C times n as a minimum degree condition is sufficient was proved by Ostus and Kuhn. These are kind of a side results. So for the problem that I will talk about, it maybe we should have some standard definitions. So capital T R minus 1 n is the Turan graph, which is a complete R minus 1 partite graph with n vertices and R minus 1 parts, and I will use frequently the notation that it has T R minus 1 n edges. So the starting point of our work is an old theorem of Erdős, Goodman, and Pósa, who proved that if we have a arbitrary graph on n vertices, I will use always the subindex n that the graph has n vertices, then the edge set can be decomposed into triangles and edges, that the total number of parts is at most n square over 4. And the reason for this n square over 4 is that if we have a complete bipartite graph, then it has n square over 4 edges, and for each of them we have to use a part, and the theorem says that if the graph has more edges, then taking advantage of using triangles, we are not doing worse than this. And for this, one has to be careful. So this trivial reasoning shows that why greedy approach can be dangerous. It assumes that my graph is that I have a complete bipartite graph with a triangle in one of the classes. If we are not careful and remove the triangle first, then after we cannot have a good partition with at most n square over 4 parts. So in this case we have to use this triangle edges to find other triangles, and somehow this is in depth why the problem is hard, that if we are doing really some stupid steps in the beginning, then we are ruining our process. Okay, and to show that this theorem is not best possible in some other sense, and even the authors realize it, as we will see later, that if let's say we have, for example, the complete graph, then we can improve the n square over 4 into n square over 6, and that motivates the part of the future work that maybe it's not fair that we count the triangle as 1 while it's killing 3 edges. And one direction how this Erdős Goodman Pósa result was extended is due to Balogh, who instead of decomposing edge set of a graph into edges and triangles, he decomposed into edges and complete graphs on R vertices. Then the analog statement holds that if there is no KR, then the only part that we can use are the edges, so we cannot do better than TR minus 1 n, and if we have more edges, then using KRs can make it up for the more edges. So the way how the problem was extended, that realizing that somehow it's a too cheap way of using large clique, is that let's assign a larger cost for a larger clique, and the natural way to assign a cost function is that the cost of a clique is its number of vertices. And Győri and Pósa 10 years later proved that if R is at least 4, then the cost of decomposing a graph into edges and R cliques is twice the Turan number of R minus 1, and one can compare it to the Balogh result, where the Balogh results is saying that we need at least T R minus 1 and edges or parts. Then here this factor of 2 is showing up, that cost of an edge is now 2, and it's an extension of the previous result, because now cost of clique is not the same as the cost of an edge, but R. Okay, and they left open the case when R is equal to 3, and it was settled asymptotically by Kral, Lidicki, Martins, and Pahova, and precisely with adding some additional people. The little of 1 in the formula means that the result is valid only when n is sufficiently large, and their proof used the method of flag algebras. So that's why one needs R sufficiently or n sufficiently large. Just repeating. So if we want to rephrase this Győri Pósa theorem, then we can rephrase the way that if we are using many of the cliques, then it means that we try to find many pairwise edge disjoint R cliques. So we can introduce this new RGS measuring it, and the Győri-Pósa theorem can be rephrased the way that if we have k extra edges compared to the Turan graph, then the number of pairwise edge disjoint R cliques should be at least this 2k over R times R minus 2, and that can be justified by looking this calculation. I don't want to say just in case somebody wants to check it. And this reformulation motivated Győri in 91 to have an improved lower bound on the number of pairwise edge disjoint cliques, that it should be at least 2 times k over R and having asymptotic. So if we compare it to the previous bound, then we can see that for R is equal to 3 is the same formula, and it's a sharper formula when R is bigger than 3. So because for R is equal to 3 is the same as before, then the conjecture was proved by the flag algebra people. So one of the main results of ours is that we proved Győri's conjecture for arbitrary R, and we didn't use method of Frege algebras. And note that I probably should have said it at the motivation of the Győri's conjecture that it has at least two best possible values. One of them is when k is equal to 0, because if we don't have a kr, then the formula says that we need to have 0 of them. And the other extremal case is that if the graph is the complete graph, then one can do a substitution and then see that that formula is again best possible. But for other case, the values should not be the same value. So in the range between k and the complete graph, k is equal to 0 and the complete graph is somewhat wide open. Partial result is that if k is little o n square, then the number of edge-disjoint cliques should be about k. And if somebody knows the regularity lemma, then it's probably easy to prove, because so this comment is for people who knows the regularity lemma. Because assume that we have Gn. If we apply the regularity lemma, then we get a cluster graph. Let's say I do it just for r is equal to 3. If the cluster graph contains a triangle, then it's standard to prove that one can find quadratic many pairwise edge-disjoint KRs, in this case triangles. So the conjecture is proved. And if the cluster graph doesn't contain, let's say, a triangle in this case, then by stability theorem, we know that it should be close looking like as a bipartite graph, and stability argument can help to find the number of KRs. So by now it should be like a standard homework question for a graduate course which covers regularity lemma. But for other range of k, it is not clear what should be the truth. One interesting partial result is due to Győri and Keszeg, that if we condition on that the graph is k4 free and we have n square over 4 plus k edges where k can be anything, certainly there is a limit because we assume the k4 freeness, then the graph contains k pairwise edge-disjoint triangles. But somehow their proof is kind of ad hoc, so it doesn't seem to generalize it for larger case when instead of, let's say, k4 we have k5 free graphs. And the similar claim is far from being true if we don't condition on k4, as one can cook up examples where the number of triangles is significantly less. Any question on the results up to this point?
Rödl, do you have any conjecture about the value? Like, do you have some external construction maybe?
No. No, I actually didn't work on the problem. So even we didn't put up any conjecture. So it's completely wide open. But my guess is based on people work on people on the audience that it should not be a linear function.
Shouldn't be.
Shouldn't be.
Oh.
Maybe you can approximate with a piecewise linear function, but like for the triangle density, when the triangle doesn't have to be edges when they are kind of bumpy or
Piecewise concave.
piecewise concave, and so it's but that's a different problem. Not clear how far they are, but so the other result that I want to talk about it when we don't restrict on the decomposition. When on the we don't restrict the clique sizes of the decompositions. So now we allow to have decomposition into arbitrary cliques. We also have a cost functions. Initially, let's have the cost function of a clique to be its number of vertices. Then the problem is reasonably easy. As soon as it was announced by Cotton and Tarjan at a conference, then 3 groups of people quickly proved it, and the proof is, at least some of the proofs is reasonably easy, like elementary, not too long proof, which states that for every graph there is a decomposition into cliques, that the weight of the decomposition is not more than we get from the complete bipartite graph. We call it the factor of 2 is there because the cost of an edge is 2, and for the complete bipartite graph we have to use edges. And their theorem says that the worst possible case is the complete bipartite graph. And it raised the question that what is a challenging way of assigning weights, and sometime after people, maybe Erdős as well, proposed that what about giving weights that the weight of a clique is the number of vertices minus 1. And note that the problem is suddenly becoming much harder, because let's say I have a complete bipartite graph and I add one edge, then I use a triangle to choose the edge, then for the rest of them are using edges. So if I compare to the n square over 4, then I save 2, because with the triangle I cover this 2, but the weight of the triangle is also 2, so it's XML. So now the unique XML is not just the complete bipartite, and then if we have more edges here, then for each of the edge we have this plus minus. So it shows that why the problem suddenly becoming much harder, and with the previous problem we didn't have this issue, because then it was minus 3 and 2. So Erdős conjectured that the worst case order should be the complete bipartite graph, and that was actually the main motivation of the Győri paper, because their result implies that the Erdős conjecture is true for K for free graphs, and the other main result of the lecture with that 5 of us we asymptotically prove the Erdős conjecture. So it means that we didn't prove the n square over 4, but with a factor of 1 plus little o 1. So in the rest of the lecture I will talk about related problems and some of the ideas of the proof of the result. So some extensions of the results is coming from a more general problem that given a graph then we can consider not only the edges, but like what is an extension of an edge is a clique. So if we have a graph G, then let's say we can have consider the triangles which are subgraph of G, and we can say that we want to cover the triangles by cliques. Let's see what is written. So let's say that we want to cover by K force or decompose. And what is it we want? We want that all the K4 that we are using are actually subgraph of the graph, and the other is that every triangle there exists a unique K4 which contains it, and the rest of the triangles are covered by a triangle. So does this decomposing problem make sense? So original problem was that we have a graph, we have the edges, and we want to decompose the edge set into triangles and edges. So one can generalize the problem that we look the triangle set of the graph, and we want to decompose them into triangles and K-force, where then obviously we need that the K4 is subgraph of G, and for every triangle there exists a unique K4 or K3 from the decomposition list which contains it. And the other question could be that what's happening if instead of decomposing we want to cover them. It's kind of a dual problem. Okay, and one can ask that why do we work with this weight? So what's happening when we have different weights? So in general we can just say that we have a cost function that for each clique size we assign a cost function, like we had the number of vertices of the clique, or the original results were that all the costs were 1, or number of vertices -1. So there's just one general setup. The other important issue is that this problem decomposing is kind of hard. What about if we want to do a fractional version of the problem, do a fractional decomposition or fractional covering? So what does it mean that we have a fractional decomposition? It means that for every clique that we are using in the graph, we have a weight between 0 and 1. And then let's say we want to decompose the edge set, then we want that for every edge the total weights of the cliques which contain this edge is exactly 1. So if we just have a decomposition, then the weights are 0 and 1 because the clique either counted or not. The fractional version is that they don't have to be integers. And actually that was Mike's idea, that he likes optimization, and in optimization problems the non-integer version of a problem is always easier because one can run some linear optimization methods, and certainly there are some inequalities that minimal fractional decompositions are cheaper than the integer. And if we prove something about minimum decomposition, then we have to hope that minimal decomposition is not much worse than integer decomposition, but it's not given. Any question on this? I didn't say too much concrete things. I just like to introduce slowly some concepts. And then the main trick that we are using is the so-called symmetrization method that should sound familiar, at least some versions. It was first applied by Zykov in 1949 when he not only proved Turan's theorem using the symmetrization argument, but even proving the following theorem that if in a k-free graph we want to maximize the number of krs, not only the number of edges but the number of krs, then the best thing to take is the complete k minus 1 partite graph. That's exactly Turan's theorem when r is equal to 2, and proof is practically along the line that we take two vertices that we don't have an edge between, and then we look the neighborhood, and we either change u to be v or change v to be u. The change means that we are replacing the neighborhood. So like if we change u to v, then what we are doing that we have u v, that's the neighborhood of v, that was the former neighborhood of u, but the current neighborhood of u is this one. And then one can observe that we didn't create a new clique. So if there was a clique before, then it's still there is one, but we don't create a new clique because this was a non-edge. So that should be a standard, or one of the standard ways to prove Turan's theorem. And I mean, I'm not saying the complete proof, but the idea of the proof is now that given a graph, it doesn't contain a kk, we consider moving u to v or v to u, and one of them has more edges or not less edges at least, and then we make sure that u and v are clone of each other, and then we keep doing it, and at one point we should arrive to a complete multipartite graph, and if we reuse the problem to complete multipartite graphs, then we can do some optimization. So that's the idea, and then that's what we do in R proof as well. Instead of, sorry, I should wrote more things. So instead of doing vertices moving one by one, we define an equivalence relation, and then we put that two vertices are equivalent to each other if they are already clones of each other, and then we symmetrize sets of equivalence classes, and do the same type of trick. This has some advantage. For example, we can make sure that the process actually stops. And what we claim that if we look the two graphs, both GU to V and GV to U, then one of the graphs is more optimal for our fractional setup than the original graph. So it means that we can do one of the symmetrization steps, and that's the point where we need the fractional version, because for our problem setup, we couldn't have this for the integer version. For Turan's theorem, it works with the integer versions, but for this, for some technical reasons, doesn't. So that's one of the key ideas. The other key tool is that for at least some particular setup, Huxell and Rödl, using the regularity lemma, proved that the number of vertex disjoint or number of edge disjoint cliques in a graph and the number of maximum number of fractional edge disjoint cliques are not differing more than epsilon n square. So it means that if we solve our problems for the fractional setup, then we don't lose more than the error term. So that's one of the main reasons that in our results we have the little one error term. So the comments under this page are related to the this problem. So when instead of covering, let's say, or decomposing the triangle set or the edge set, we want to do, let's say, the triangle set, then such theorem didn't exist as Huxell and Rödl, so we had to prove it, and we couldn't prove everything. So at the very last few minutes I will explain what steps did not work through and also state more results. Is any question on this? Because now I kind of talk maybe too many things.
It seems like you play with the prime optimization question. I was thinking about the duality question, because it's a strong duality with a fractional packing number or something to something like fractional matching or.
Yeah, there is some duality parts. I try to avoid the writing up the linear programs in this lecture, but if you look up the paper, in particular the 5-author one, then we write many things in the setup of linear programming, and there are some dualities as but I thought that it would be too technical to write up the formulas for this. Okay, so I try to give more details and maybe try to become a little bit clearer. So let's go back to the first result. So we want to prove that if we have the Turan number plus k many edges, then we can find many pairwise edges joint complete graph KRs. So first we do this symmetrization step that I had one of the boards, but with the sets U and V, and we work with the fractional setup. So we want to find the fractional cliques, and the symmetrization gives that if we start with a graph G, then we can change the problem to that we can assume that the graph G is instead of a graph G, we can have a complete multi-partite graph H. And the other slight difference compared to the standard way of using symmetrization, that let's say when we run Zykov proof to say that we want to maximize the number of edges, we have a different goal function. It is the fractional number of pairwise edges joint KRs minus 2 over R times the number of edges. So this is the function that we want to optimize, and during symmetrization we want this function to get smaller and smaller. The reason is that we need like linear combinations of two functions. That if we look at our theorem, then the number of these edge-disjoint cliques that we want to prove is depending on the number of edges of the graph. And if we do the symmetrization, then we actually don't know how the total number of edges changes, because it could be that it drops a lot or increases a lot. So we have to factor this as a goal function. The second step is that when we arrive to a complete multipartite graph, then we still have to prove that whatever we want to get is correct. I didn't do the computation here, but if we prove the inequality from the lemma, then it implies the theorem. And in the case when we had the proof for Turan's theorem, then it's a standard optimization exercise. I'm sure that in high school you did something similar. Somehow for our projects, maybe we just slow, but to do the symmetrization, it was less than a week to prove the handle the case of a multipartite graph. It took 2 months, because somehow there are many multipartite graphs, because we don't have anything. We don't know the number of classes, the sizes of the classes, and if I give you a complete multipartite graph and ask you to compute the fractional number of pairwise edges and KRs, then it's not that easy, and we have to compare it with the number of edges, but we managed to overcome. So that's the shorter proof. So somehow the additional challenge that one has to do with the induction, that let's say that if I have a complete multipartite graph, want to remove a class, then with the class I not only remove edges, but like remove larger cliques, and then after the removal, whatever I get is not a complete multipartite graph anymore, so I cannot do induction statement. But a proof is not that long. If somebody wants to look at it, maybe we can read it. I try to keep some ideas about the proof of the other result when we can decompose into arbitrary cliques. So recall that we have a cost function, and now I introduce notation for the two general problems that we look. So the T stands for whatever here is the triangle that we want to look the KT sets of a graph. So given a graph, then it has a family of K T's, and we want to look the two problems. One of them is decomposition, so we want to find a family of cliques that each KT is part exactly once, and but also the cliques are subgraphs of the graph. And the covering is that we cover everything at least once. And actually this was our starting point when we were at IBS. This conjecture of Dow, Milenkovic and Puleo, that if we do the clique covering problem, then the Turan graph is the reverse graph. So that the generalization of the edge covering problem is going through, and this Dao, Milenkovic and Puleo solved the problem for t is equal to 3, and if we compare the general problem with this Erdős Győri problems, then the difference is that in the first conjecture the weight functions were all 1, and in the decomposition problem into cliques, here the 2 means that it's just the original Erdős problem. We already have the weights. Okay. So some of the general results that we proved is that for both the decomposition problem and the covering problem, the symmetrization arguments work, so that from a standard graph we can reduce the problem for a multi-partite graph. So this was done by Mike. For me it was miracle. I had to check every step by step, because for the covering problem, because it's not so delicate, it's believable, but for decomposing it's kind of a miracle that in the symmetrization it actually works out. I actually double checked it before my lecture as well, just to make sure that it works. But the next step is that assume that we have the complete multipartite graph, then in what cases it is true that let's say for the covering problem we cannot do better than the two-round problem, and here are conditions on the sequences that this the difference of the two consecutive members of the sequence cannot be larger than the first element of the sequence. Note that for covering the sequence starts at t, and that's also, it suggests that if we start at we can assume that ct is 1, then the best what we can do that ct plus 1 is 2, ct plus 2 is 3, so it's kind of showing that the weights of the Erdős conjectures are kind of fitting exactly. So if he instead of 2 he would put 2 plus epsilon, 3 plus 2 epsilon, then the methods would not work. So it's interesting that it's coming out to exactly that point. And the other interesting thing that again having the complete multipartite graph suggests that it's easy to prove that then the two-round graph among them is the optimal. So for the decomposition problem, we could not do it in general. We could do it only for the graph case, but this is the case where the Erdős conjecture was, so that's also lucky. But for larger T, we couldn't say that among the complete multipartite graphs, the two-round graph is the optimal. And there needs an additional step to prove an analog of the Huxell-Rödl theorem that the fractional decompositions or the fractional coverings are not far from the true, and for the covering problem we managed to do this, but for second I thought that we didn't manage to do 4 also. I get unsecure. So maybe we managed to do 4 or I did a typo when I did my notes.
So in the previous slide, is this G tilde just the weighted reduced graph, the blow up of it?
So the no, not necessarily. I see. So that's a big difference compared to Huxell and Rödl, because in Huxell and Rödl proved for the same graph, and here we proved that that there is a graph which is in the fractional setup is not doing better. Your question was that if G tilde is the reduced graph. Okay, you are asking into proof in page 30. I think it's likely. I haven't looked at the proof in that detail for this lecture. It should be likely, but I think it's just repeating the previous things. Yes, so actually here there is a new information. So the Huxell-Rödl actually goes through for the decomposition problem, that the weighted decomposition is the fractional is not much worse, but for the covering the proof didn't go through. And there is some reasons for it. The reason is that let's say that if in the decomposition in the proof somehow we have some extra edge, then we could add it to the decomposition. But if here in the covering, if we remove an edge, then we have to remove the entire thing, which might contain the edge. Okay. Sorry, I kind of get confused with the end, but anyway, I plan to stop here.
Thank you. Any questions?
Yeah, so I think throughout this talk you were discussing the decomposition or clique covered by cliques.
Yes.
And I wonder if there are anything interesting, like if we generalize triangles in another direction, meaning that I want to cover things by 4 cycles.
Could be. So I'm not aware of if the literature studied it, or so I can't say anything, but I think there could be interesting questions. I mean, probably they were not studied heavily because the cliques were the basic cases, and somehow the only movement before our work recently was by method of Leg algebras, which has some limitations, so like they don't work for larger cliques, and they work on in the positive density setup. So one might find a good problem.
Was there some analogous theorem for edges, so decomposing graph into edges and C4 and K22? There's some theorem, right? Just like edge Goodman Pósa. Like I don't know, some linear algebra proof, or like something, maybe.
Could be.
It could be.
I mean, it's a natural question to try to decompose graphs into to others. I mean, if you look the now big literature on design theory, they actually the general results of Kostochka and maybe follow-up are doing that. If given a sufficiently dense graph or pseudo-random graph G, then they decompose it into, actually they decompose it into arbitrary graph. I think that's the extension of the design theory. That the design theory is decomposing into cliques under some conditions. They decompose pseudo-random graphs into some other graph, but that's very far from what I'm talking about, and they are certainly at different depth.
So for some of the theorems, when you use symmetrization, maybe your theorem is true for all n, but then when you use regularity lemma, maybe it's true only for large n.
Yeah, so the for the fractional versions, the result should be true for every n. There is no reason not to, and the big n, the little o1 versions are going from the fractional to the integer. Maybe there are other ways to move from fractional to integer. I think Beck-Fieler theorem has doing this by moving things, and then the number of so I think it's kind of standard that if you have a fractional solution, then you can try to move toward the integer, and then when you get stuck, then the number of things which are not behaving properly is smaller. But I don't know how to do it for graphs.
Any other questions?
So following up on Zykhov's question, so do you think, like, say, we decompose a bipartite graph into KSTs with some similar costs defined in this way would be a problem of a similar taste?
I think the problem could be interesting first, because we get into this design question, you have to check if they follow anything from designs. The second, that I think it's not similar case, because the symmetrization argument is the dense Turan. So it's like when you say that Turan's theorem is similar taste as a bipartite Turan problem, in some sense you can say it's similar taste, so in some sense similar, but the method not clear. You have to think, because you actually didn't say that you want to do the degenerate setup. You just said the multipartite setup. I know that like for multipartite graphs, Turan's theorem behave differently, but So it could be very likely that even the basic questions which here were like trivial in the 60s, like this Erdős, Pósa, Goodman was, I think even then to be counted as an easy result. They might be already hard for the multipartite setup. Because if you just try to look at the literature, that for three-partite graph was the XML number for triangle, or then it's already not that easy. Other question?
Any other questions? If not, let's thank the speaker.